Hello, and welcome to the Exam 1 review for summer 2017. So this is going to, these are going to be the free answer portions of the tests. So you'll see an example of each of the ones you need to study. There will be other multiple choice questions. We'll go over those in class, but those are mostly going to be the sort of the central ideas, stuff like that. So the things like trends and whatnot, things like solubility and melting point, things like that. So onto the free answer part. So isomers, stuff like that. So in this case, what I'll do is I'll give you a structural, or I'll give you a formula, and you need to, and how many you need to draw. So for that, I think it's 2. So with that, but it must contain, in this case, it must contain a functional group. So with that, in this case, it's an alcohol. It could be any of the other functional groups. So with that, so just make sure that they are in fact distinct structures. So with that, so for here, the way I usually do it is you've got 3 carbons, right? So we usually do, I usually start with just putting the carbons in a straight line. So with that, so and I need to have an alcohol group. So you need to have an OH. Say here, so then you just fill in with the rest of the hydrogens. Okay, so that's it. Now if you were to draw this, that structure, these are actually the same structure. It's just this molecule has just been flipped to make this one. So that wouldn't work. So what you actually need to do, and you have to take into account the bond rotations and things like that. So the molecule rotations, bond rotations, whatnot. So putting the OH here, there's no way that you can flip this to be here. So then you fill in with the rest of the hydrogens. Okay, I don't care if you do a condensed structure like this or a skeletal structure, whatever you need to do. So these are the 2. They have the alcohol group that's required, and they have this formula. So the overall formal charge. So what you're going to do is I'm going to have the an arrow pointing to a specific atom, stuff like that, and I want you to get the formal charge for that. And then what I need you to do is just calculate the overall charge on the molecule by just adding up those formal charges. You can just assume every, and I say in the this is actually the wording of the question. You can indicate, any non-indicated atoms just have a formal charge of 0, so you can just ignore those. So for here, right? So with that, you're going to want to split each bond. So each atom gets 1 electron. So the oxygen looks like this after you split it: electron, 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 and then the lone pair. So if you count over, you need to start with the valence electrons of the oxygen, which in this case, if you count over, it's 6, and then subtract how many it has now. So 1, 2, 3, 4, 5. So the overall formal charge is +1. So since this is the only indicated atom, right? So with that, the overall charge is going to be +1. So what's the hybridization of the indicated atom? Remember, this is going to be SP, SP2, or SP3. Those are the only ones we deal with. So with that, and so this is the number of bond sets plus lone pair sets. Right? That'll tell you how many letters there are, and then you can go from there. And then it goes S, and then just add P's. Okay, so with that, so for this one here, you have you don't have any. So 1, 2 bond sets plus 0 lone pair sets. Okay, so you need 2 letters. So it's S and P. So it's an SP or SP1, however you want to do that. So for here, you have 1, 2 bond sets. You have 1, 2 lone pair sets. So you need 4 letters. So it needs to be SPPP or SP3. Okay, so for here, determine the number of pi and sigma bonds for each indicated bond. So this bond here, right? You're always going to have 1 sigma bond. Always, always, always. It just depends on how many pi bonds. So for here, the first one is going to be the sigma, and then the next one is going to be a pi. So here you got sigma pi, so you have 1. And then for here, for this bond, you have 1 sigma. That's the first one that goes down, and then no others, so it'd be 0 for the pi. Circle the molecule in each pair that is the most acidic. Okay, so when you're looking at So these are going to be the acidic hydrogens here. So you look at, the first thing you look at is what that is, the atom is sitting on, or what's it's attached to directly here, because you want it to go to iodine, right? Because if you think about the mineral acids, HI, right? So for that, you want this thing, the acidic hydrogen, to be as close as you can on something to iodine. Okay, phosphorus is one lower on the periodic table than nitrogen. Okay, so this is going to be the more acidic molecule. Now, when you're talking about after that, then what you're looking for is electronegativity. Okay, so for atoms, with the acidic hydrogen in the same row, so as you go across, right? So CH bonds are going to be a lot less acidic than HF bonds. So that same goes down on a column. Okay, so the closer you get to iodine, the more acidic it is. Also with hybridization, the more S character, right? So this is 50%, right? Because it's 1S and 1P. Here's 1S and 2P, so this is 33%. And here it's 25% because there's 1S and 3Ps. So the more S character you have, the stronger the acid. If you have any sort of adjacent pi bonds, so it doesn't matter if it's a carbon-carbon double bond or it's a carbon-oxygen double bond, it's going to be more acidic. Like that. So compared to just a regular alcohol that has just single bond next to it, so here you've got a double bond. So the other thing is you have these inductive effects, and so here you're just dealing with electronegativity. The other one we're trying close to HI, but here, right, you have the regular carboxylic acid, but if you add a chlorine right next to it, it becomes much more acidic. Now, if you move that chlorine away, the inductive effect goes away. You have to okay. Okay, so indicate if the reaction favors the forward or reverse direction. So what you're going to want to do is this number wants to go up. So you want to go from a strong the stronger acid to the weaker acid, right? So you want this number to go up. So this one's going to go forward. So it's going to favor this product here. Okay, this particular case makes sense because it's hydrochloric acid plus something like sodium hydroxide, an acid base, it's going to react. Okay. So for the condensed structure, remember with that, so I'm going to give you a structure like this. Okay, so one of the things you can do is you have sort of the longest stretch of carbon, so 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5, like this. And so now here's a double bond, so you need to indicate this. So between this guy here, and there is an OH hanging off of here, so you can go ahead and draw it hanging off of here. Same with this one here, the CH3. You can have it like this. Okay. Now let's start putting in the hydrogens, right? So this has 3, so CH3. This one has 1. Right? You've already indicated that. Here you have CH1. Here you also have one CH. Here you have CH2. So this is perfectly fine. The other way that you can do it is CH3, CH, right? And then anything on the parentheses is assumed that's going to be there. So CH, double bond. You have to show that double bond. CH, CH2, OH. Or, I mean, you could probably get away with just CH2OH. That's fine. So like that. And so I'll take either one. You don't need this arrow. So for the skeletal structure, so what you want to do is you want to get rid of any of the CH bonds. Now the OH you have to keep there. Right? So with that, and so you can put in your dots. Just transcribe where a carbon is for dots, and then connect. Double bond O, OH, and that's it. This is totally fine. You could do a sawtooth, or you could just do it like this. I'll take either one. Okay, so for the resonance structures, first thing you got to do is you need to look to make sure everybody's eligible. It's usually a good thing to go ahead and draw in all of the hydrogens in the molecule, and that'll help you see what's going on. So here, in order to be able to participate in the resonance structure, an atom either needs to be charged, it needs to be part of it has to have a lone pair, or it needs to be part of a double or triple bond, stuff like that. And so here, right, so this one has charged, these two are part of a double bond, so they're eligible. This one's part of a double bond, so that's eligible. And this one here, notice how it has just 4 single bonds, no charge, no nothing, stuff like that, and so that one can't participate. Okay, and so you look here, so general rule of thumb for resonance structures is take a look at the charge and figure out what's going on. So this carbon only has three bonds, it wants a 4th one. So what it can do is we can move this double bond up there to make this resonance structure. Now we haven't done anything with this double bond, so it just stays there. This one goes here. Now this hydrogen has a plus charge because it only has three bonds, so we can move this double bond over here. So we can make this. You know, we could move this bond back down here, but you would just generate this structure again. Here. Okay, and now that this one only has 3 bonds, and so we'd love to be able to go over here, but we can't because this one isn't eligible. And so once you get to the end of your eligible, you either get to the end of the line of eligible atoms, or you come back to the beginning if you have a ring, stuff like that. So since we've come to the end, there's no more eligible atoms, so we stop. Okay, so for here, I'm going to see which way the polar covalent bond is indicated, and you can do that either with the symbol or these symbols or the arrow. And then I also want you to draw the overall, show me where the overall dipole is on the molecule, stuff like that. So if the molecule doesn't contain a dipole, write no dipole. Don't just leave it blank, because if you leave it blank, I'm going to assume you didn't know. So like that. So here, right, oxygen's more electronegative than oxygen, so that arrow is going to go like this. The other way you could do it is like this. Remember the plus, the cross hatch is going to be on the plus side. This will be the negative side. So same thing here. It does not matter if it's a double, or triple bond or single bond. It's just looking at the atoms. Now you could do arrows, you could do symbols. It doesn't matter. I'm just doing both just to show you, but you could do either one. Okay, and then the overall is just going to be halfway in between these arrows, so it's going to be like this. So overall dipole. So there we go. Okay, so for here, determine which pair of the molecules gives the corresponding IR spectrum. So you're going to be given the chart, okay, and so you look at this and you say, okay, so for here, this one, of course, you look on your chart, and it could be a couple of different things, but mainly if you look at which one of these molecules, it's going to be an alkene, okay, and then this one, again, it could be a couple of different things, but this one is a CH bond coming off of the double bond, stuff like that. And so since we're looking at a double bond, this one doesn't, but this one does, and so it's going to be this one, right? So this bond here would be the 1650, and then these hydrogens coming off of here, those would be the 3050. Okay, I just need you to circle them. I don't need you to necessarily label them, stuff like that, but to just illustrate what's going on. So but don't forget, if it's not listed, okay, now you can assume that the alkane CC and alkane CH signals are there. I'm not going to list those because it gets it confuses students, stuff like that. So because they overinterpret it, so you just assume that that's there, and you're just looking for the other functional groups. But if I don't have a signal listed, there's a reason. Okay, so you have to be careful. Okay, now for this one, circle and name the functional group. So alkanes, cycloalkanes, and benzene groups don't need to be listed, so like that. So now here, this is Symbicort. This is a steroid, so like that. So now this is from an older book, so like that, and they had acetal listed. So I'm not going to have anyone here that you guys aren't going to see that's on the list. Okay, so you just start at one end and work your way across. Okay, so here, this is a carbonyl, C double bond O. It's got carbons on either side, so that you circle this, you say, hey, that's a ketone. These two here, now it's part of a 6-membered ring, but it's not double single all the way around. So these are in fact both alkenes. Alkene. Okay, now there's a cyclohexane ring, but I don't need to show that. Okay, here, this is an OH with with no C double bond O next to it. So this is an alcohol, nor is it part of a benzene ring. Here, that the acetyl's there. Here, this is also another ketone. You're saying, hey, wait a minute, there's an OH next to it. Yeah, but there's a CH2 in between it. Okay, so there's a carbon and carbon on both sides, and so this is an alcohol. So they are in fact two different groups. Stuff like that. So no other group, right? These are just hydrogens. That's a methyl, and that's it. So this is Toviaz, a physotieridine. It's targeted right now for overactive bladder. So with that, so you have a C double bond O, you have a CH on this side. So you have a carbon on this side and an O carbon on this side, so that makes this an ester. Okay, so now this is a benzene ring, so I'm not. You don't have to circle and label that. There is an OH next to the benzene, but it's not actually on the benzene. If the OH was here, so if it came up directly OH, that would be a phenol. But this is, in fact, there's actually a CH2 in here between. That makes all the difference. And so this ends up just being a regular alcohol. Okay, so come down here. That's a benzene. Don't have to worry about that. That's another benzene. Don't have to worry about that. Come over here. It's a nitrogen without a C double bond O next to it. So that makes this just a regular amine. There you go. Good luck.